let's now take a quick look at nuclear fusion. So fusion is a process where two smaller nuclei come together and fuse into a more massive nucleus. You should care about fusion because that's where the sun gets its energy from, and and that's how ultimately we get the energy we use here on Earth. So a typical fusion process might look something like this. So if I start with, say, hydrogen, and it turns out you can fuse hydrogen with deuterium, which is the isotope of hydrogen with an atomic with a proton and a neutron in the nucleus, so a mass number of 2. This fuses to helium-3, and you also, it turns out, you get a photon out of that. This is one of the fusion reactions that happens in the sun. And so, just a word about what physicists are trying to do with this. So it's an active area of research to see if we could perhaps harness fusion on Earth. It's a area that it'd be awesome if we could do it, but there are still enormous technical challenges, including with how do I confine in, say, a plasma the nuclei so that they actually fuse with each other. But maybe that's a problem that you'll contribute to solving one day. The last process I want to talk about is nuclear fission. So fission generally happens when you have some very large nucleus. It comes in and absorbs a neutron, and then somehow and then becomes unstable, and then breaks apart into less massive nuclei. I'll go to a slide where I sort of have a cartoon of what this, you can sort of think of this as looking like. An example of fission is the fission of uranium-235, and that's a process that looks like this. So we have a neutron coming in plus a uranium-235 nucleus, and then that undergoes fission, giving barium 14156. And krypton 9236 plus 3 neutrons. So you actually have the wherewithal to calculate how much energy is released when this happens to one uranium nucleon. If you go and think about, we'll do that as a whiteboard exercise actually. I'll give you the masses of the various nuclei. You can also look them up in handbooks if you need to. So as you think about that exercise, I'll tell you that this is a process that releases energy. You should think about what you might expect for, are the initial things more massive, or are the final things more massive? So think about that, and then we'll come back and I'll discuss it. So this is a case where the mass of the initial things is greater than the mass of the final things. So if you want to think of it loosely, you can think about you can say that some of the rest energy of the initial particles gets converted into other forms of energy. So let's say the kinetic energy of the fission products. So we can think about how much energy is released in the following way. Right? So we can look at the delta M, which is so the final minus the initial mass. And if you go through the calculation, the result that I got 0.186 and change unified mass units. And then the energy released for one nucleus undergoing fission per nucleus. That turns out to be delta M times c squared. So that change in rest energy, and that I got 172 mega electron volts. Now, it might be a little tricky to put that number into context, but it turns out you can go and look up some chemistry data for how much energy is released in a typical combustion reaction. Let me go and write that down once I erase the board. So consider burning methane, aka natural gas. Right, so you've got methane plus oxygen goes to carbon dioxide and water. So the energy that it turns out you get out of one molecule of methane, energy from one molecule turns out to be approximately 8.33 electron volts. So that's an orders of magnitude different, right? Because we were just talking about mega electron volts for about 170 something mega electron volts for the fission of a uranium nucleus. And so that gives you a sense of the scale of how much more energy you can get out of a fission event than burning stuff. Let's wrap up by going to my laptop. I just want to briefly show you a few things involving some applications of fission. So a couple of things I just wanted to show you about fission. As I mentioned earlier, in a fission reaction you have a neutron that comes in and that starts things. It turns out, for sort of reasons that are not obvious, that slower neutrons are more likely to cause fission. So what we're plotting on this graph on log scales, log scales is here the neutron incoming kinetic energy. And then here is something called the cross section for fission. You can basically think of this as the probability of a fission reaction happening, and you can see that it drops off the higher energy my neutrons are. You can sort of loosely think about this as sort of the faster a neutron is whizzing by a uranium nucleus, the less time it has to interact with the uranium, and that how loosely why you can think of it as having a smaller reaction probability. So why this matters is that it actually comes into the design of nuclear reactors. So this is the schematic for a pressurized water type of nuclear reactor. I don't think we have any nuclear reactors for generating electricity in this part of upstate New York, but you might live in you might come from a part of the country where nuclear power is still being used. Where the fact that you want slower neutrons comes in is that the the fission reactions happen actually underwater. It turns out water is really good at absorbing neutrons, or not absorbing neutrons, but in interacting with neutrons to slow them down and make them more likely to induce induce fission. And so just a few things, right? What happens in a typical reactor is the heat from those fission reactions causes water to boil and make steam, and then the steam turns a turbine, and then that's what spins a generator to make electricity. Now, nuclear power, right, there's still all sorts of issues that this raises. Like, what do we do with the highly radioactive waste that comes out of that is a byproduct of fission reactors? How do we make these things safe and avoid situations like the 3 Mile Island incident back in Pennsylvania in the 70s, or more recently the Fukushima Daiichi accident that happened following the tsunami in Japan. Um, so how do we also prevent sort of nuclear reactor waste from falling into the hands of, say, terrorists or people who would do bad things with that? On the other hand, right, is nuclear power something that we should be thinking about as we try to move away from fossil fuels? And I think an understanding of the physics is helpful for being able to participate intelligently in those critical policy debates. Now, talking about fission, I would be remiss if I didn't mention perhaps a great destructive thing that one can do with fission, aka nuclear weapons. So this is a schematic of the type of atomic bomb that was used on Nagasaki in in August 1945. I don't think I needed to tell you about how destructive these things are and how, right, with nuclear weapons in general, humanity has the capacity to destroy itself several times over. But again, as you think about contributing to the discussion of, what do we do with all our nuclear weapons? How do we prevent nuclear weapons proliferation? Right? These are questions that understanding the physics can help you answer. So we're ending here on a perhaps a rather sobering note, but at the same time, I think it's a matter of, right, of knowledge is power, and that knowing about the physics involved can help you contribute to maybe solving some of the issues that for both for good and bad that nuclear energy and nuclear weapons issues pose. At the same time, right, there are some incredibly useful things one can do with nuclear physics. We haven't talked at all about nuclear medicine, but perhaps you've had a family member who's had radiation therapy to treat cancer. Physicists are involved in doing that, right? So I think, if I recall, one of the posters out in the hallway is an IC physics alum who's gone into doing medical physics, because you need people with physics knowledge to go and run the treatment machines that are in hospitals. So maybe that's something you might consider as a career, if that's something that appeals to you. And so we come now, I think, to the end of the course. I'll be with you on Monday for a synchronous session. It'll be lovely, I hope, to see as many of you then as I can. It'll be nice to just say hi to each other, and I'll answer, of course, any questions you may have about the final exam or anything, frankly, we've discussed in the course. But so yeah, so I look forward to seeing you on Monday if you can make it, and have a lovely weekend.